So we know what limits are. But if we really want to do math, right, we need to compute with limits. We need to figure out how to figure out what some particular limits are. Here are some basic facts about computing limits. Some limits are just plain obvious. If you take the limit of a constant function, well, all of the values of that function are exactly the same. What's that function doing? Well, it's just sitting at that same value. So the limit of c is c. What's x doing as x goes to a? It's going to a. That almost makes you feel stupid to say that, doesn't it? There's two others that are fairly obvious, I think, which is that the limit as x goes to infinity of 1 over x is 0, and the limit as x goes to minus infinity of 1 over x is also 0. If you don't quite see that, here's a picture. You can see that as you make x bigger and bigger, what's happening to 1 over x? It's getting smaller and smaller, closer and closer to 0. Same thing with going to the left, except that then 1 over x is negative, but still, you're going to 0. Now, with just these particular really, really obvious limits, we wouldn't be able to do much. So let's see how to combine our knowledge of some limits to figure out some other limits. The idea here is that limits play nice with algebra. What do I mean by that? Let's suppose we know two limits. I've got two functions, f and g. I'm looking at their limits at the same point a, and I happen to know that the limit of f at a is m, and the limit of g at a is l. Then I'm entitled to compute the limits of lots of other functions too. For example, I could consider the function f plus g that I get by adding f and g, and ask what's its limit at a, and the answer is m plus l. In other words, the limit of a sum is the sum of the limits. Besides addition, we can do basically any other algebraic operation you can think of. In addition to the sum, we have really nice limit rules for differences, products, and quotients, and basically what these rules say is you could either do the subtraction, the multiplication, or the division inside the limit, or you could take the limit of each function individually and do the corresponding algebraic operation afterwards to the limits. I will say one thing that's very important is that the quotient formula only applies if you're not dividing by 0. But that makes sense, because what would division by 0 mean? We wouldn't know what the right-hand side meant anyway. Let's use these rules to compute a particular limit. If we consider the limit of the polynomial 4t cubed minus t squared plus 2t as t goes to 3. First, we use the fact that the limit of a sum is the sum of the limits to split that limit out across this plus and this minus sign. We also know that the limit of a product is the product of the limits. So we can go ahead and write each product there as two limits multiplied together. Notice the very last term I've written as t times t, right? T squared is t times t. We can actually do the same thing with the t cubed. And instead of writing limit of t times limit of t times limit of t, I'm just going to write limit of t cubed. And I'll do the same thing with the limit of t squared. What we have here is a big algebraic expression, and everything we have is one of those obvious limits. So let's just go ahead and compute those obvious limits. Okay, there we go. No sweat, right? This example might be a bit misleading, because it might lead you to think that all we did, if you compare this function that we're taking the limit of, 3t cubed plus 2t minus t squared, it looks like all we did was plug in t equals 3. Now, if that's all limits were, it wouldn't be a very interesting thing to study limits. And limits wouldn't be very useful, because they'd just be a synonym for plugging in. So what I want you to realize is that that isn't what happened. Notice we went through several steps, several algebraic steps, and we happened to get the same answer as if we'd plugged in. But what really happened is we got lucky. The function we used was a polynomial, and polynomials are among the world's nicest functions. So yeah, they play nice with limits too. Besides polynomials, there are a few other basic operations that play really nice with limits. We've seen one already. We had the limit of t cubed, and that ended up being the limit of t outside cubed. That always happens. Powers play nice with limits. And since it works with powers, it should also work with roots, you might think, and that's exactly correct. So basically all of the algebraic operations we're familiar with play nice with limits. You can do the limit before or after. I want to emphasize again, that doesn't mean that limits are just plugging in. The limit operation is a very different thing. Once we get to a little bit less well-behaved functions, we'll see where the limit concept really shines.